You use energy every single second of your life. Your heart beats with it. Your phone runs on it. The sun floods the entire solar system with it. And yet, if you walked up to the smartest physicist alive and asked them what energy actually is, they could not give you a clean answer. Pause on that. The force powering every star, every atom, every thought in your head, and science cannot fully define it. We will go from the ancient wrong answers all the way to quantum fields, dark energy, and the possibility that energy is something far stranger than anyone expected. If you enjoy the journey, like and subscribe. Now, let's go. Right now, your heart is beating, your lungs are expanding, your brain is firing millions of tiny electrical signals just so you can process this sentence. All of that runs on energy, every single bit of it. And here is the part that should bother you. Not one physicist on Earth can tell you what energy actually is. That sounds insane. We live in a time when scientists can map the surface of Mars, split atoms, and build machines that think. Energy is the most used concept in all of science. It shows up in every equation, every experiment, every technology you have ever touched. And still, the definition falls apart the moment you push on it hard enough. Ask a physics teacher, and they will say energy is the ability to do work. Fair enough. But what does that actually mean? Work is force applied over a distance. So energy is the ability to apply force over a distance. And force is mass times acceleration. So now you are 3 definitions deep, and you still have not touched what energy actually is. You have only described what it does. Picture a charged battery sitting on a table. It is doing nothing. It is just sitting there. But everyone agrees it holds energy. You cannot see the energy. You cannot point to it. You cannot remove it from the battery and hold it in your hand. The battery looks the same whether it is full or dead. The energy has no shape, no color, no texture. It is invisible. And yet it is real enough to power a car for 300 miles. That gap between knowing energy is real and being unable to say what it is made of is one of the biggest open questions in all of science. Physicists have been chasing a clean answer for over 300 years. Every time they get close, the question shifts and gets stranger. Here is what makes this wild. We are not talking about some rare, exotic phenomenon that only shows up in a lab. Energy is everywhere. A rock sitting on a cliff holds it. The sunlight hitting your skin carries it. The food digesting in your stomach releases it. You are made of it. The planet is made of it. The entire universe runs on nothing else. And yet the smartest people who ever lived, people like Einstein, Feynman, and Bohr, all admitted they could not pin it down. Richard Feynman, one of the greatest physicists of the 20th century, said outright that in physics, we have no knowledge of what energy is. He said it like it was completely normal, because in physics, it is. What scientists can do is measure energy. They can track it, they can watch it move from one object to another, change form, do work, and behave according to precise rules. The math works perfectly, the predictions are exact, but the underlying reality, what energy actually is at the deepest level, stays hidden. This is not a small gap in human knowledge. It sits right at the center of physics, chemistry, biology, and cosmology, all at once. Every science touches energy. Every science depends on it, and every science hits the same wall when trying to explain what it fundamentally is. Over the course of this journey, that wall is going to crack open. You will see where the wrong answers came from, where the right ones broke down, and where the mystery goes so deep that it starts to reshape what you think reality even is. But before we can talk about what energy is, we have to talk about what people used to think it was. And those old answers were so wrong and so confident that they held science back for centuries. About 2,500 years ago, in ancient Greece, a philosopher named Empedocles looked at the world and decided he had figured it out. Everything, he said, is made of 4 things: earth, water, air, and fire. Mix them in different amounts, and you get every substance in the universe. Rocks are mostly earth, rivers are mostly water. The wind is air in motion. And fire was special. Fire was the force behind change. This was the ancient world's theory of energy. Fire did not just produce heat. Fire was the active element. It transformed things. Wood became ash, metal became liquid, food became something the body could use. Fire was the closest concept they had to a force that moved the world forward. And for 2,000 years, this idea dominated. Not because people were stupid. The Greeks were brilliant. Aristotle, who came after Empedocles, built one of the most detailed systems of understanding the world ever constructed. But without precise measurement tools, without experiments that could be repeated and tested, the ideas just stacked on top of each other. Nobody could prove them wrong. And so they stayed. The idea of fire as a transforming force eventually evolved into something more specific. By the 1600s, scientists started calling it something new. They believed heat itself was a substance, an invisible fluid that flowed from hot things into cold things. If you held your hands near a fire, this fluid poured into your skin and warmed you. If you touched ice, the fluid drained out of you and into the ice. They called it caloric. Caloric felt logical. Heat did seem to flow. Touch a cold metal spoon and heat moves from your hand into the spoon. The spoon warms up. You cool down slightly. That looks exactly like a fluid moving. The model even made useful predictions. Scientists built equations around caloric. They designed early steam engines using it. For a while, caloric theory worked well enough that almost everyone believed it. Here is the part that should make your stomach drop. Educated, serious scientists in the 1700s were completely certain about caloric. They wrote textbooks on it. They taught it in universities. They based entire fields of chemistry on it. And they were completely, totally wrong. The crack appeared in 1798. An American scientist named Benjamin Thompson was supervising the drilling of a cannon barrel in a military factory in Bavaria. The drilling process generated enormous amounts of heat. Everyone assumed this was just the caloric being squeezed out of the metal as the drill bit into it. Standard explanation. But Thompson noticed something strange. The heat kept coming. Long after any reasonable amount of caloric should have been released, the heat continued. He ran the drill longer. More heat. He ran it even longer. Still more heat. If caloric was a stored substance inside the metal, it should run out. Metal has a fixed amount of stuff inside it. But the heat seemed endless. Thompson realized caloric could not be a substance. Something else was causing it. He published his findings and the scientific world resisted for decades. Old ideas do not die easily. It took another generation of work before the truth settled in. Heat is a behavior, not a material. And that discovery cracked open a door that would eventually lead physics somewhere far stranger. The factory was loud, metal screaming against metal. A massive bronze cannon barrel locked into a machine and a steel drill biting into it hour after hour. Benjamin Thompson stood watching, and something about the heat bothered him. Everyone around him had a ready explanation. The drilling was squeezing caloric out of the metal. That was the standard answer. Caloric, the invisible fluid of heat, escaped when metal was worked hard. Simple, obvious, accepted. Thompson did not buy it. He decided to run a test. He submerged the cannon barrel in a tank of cold water and started the drill again. The friction from drilling heated the water. That part was expected. But Thompson kept the drill running. The water kept heating. After about 2.5 hours, the water began to boil. The drill was still going. The water was boiling from friction alone, and the metal barrel showed no signs of running out of anything. Thompson ran the numbers. The amount of heat produced was essentially unlimited, as long as the drill kept moving. A substance cannot do that. If caloric was real and stored inside the metal, it had to have a limit. You cannot pour infinite liquid out of a finite container, but the heat had no limit as long as mechanical work kept feeding into the system. What Thomson had stumbled onto was a relationship. Mechanical work, meaning movement and force, was turning into heat. They were connected. One could become the other. That was the key insight, and it was massive. But Thomson was ahead of his time. The scientific establishment pushed back hard. Caloric theory had too much invested in it, too many equations, too many careers. It took another 50 years before the connection between work and heat became fully accepted, and that final confirmation came from a British brewer named James Joule. Joule was obsessed with precision. In the 1840s, he built a device that used falling weights to spin a paddle inside a container of water. The falling weights did mechanical work. The paddle stirred the water. The water warmed up. Joule measured the temperature rise with extreme care and found a precise, repeatable relationship. A fixed amount of mechanical work always produced the exact same amount of heat. Every single time, no matter what. That repeatability was the proof. Heat and mechanical work were two faces of the same thing. You could convert one into the other at a fixed rate, like exchanging dollars for euros at a locked exchange rate. That single discovery laid the groundwork for one of the most powerful laws in all of science, the conservation of energy. The unit of energy today carries Joule's name. Every time a scientist measures a joule of energy, they are honoring the man who proved that heat and motion are brothers. But here is what Joule's experiment did not answer. It showed that work becomes heat. It showed the conversion is reliable. It did not explain what heat actually is at a deeper level. It did not say what energy is made of. It just proved that different forms of it can trade places. That answer, the one about what heat actually is at the molecular level, came next. And it required scientists to look at matter in a way nobody had seriously attempted before, at the scale of individual atoms. And what they found there changed everything about how we picture the physical world. Picture a sealed metal box filled with air. Now imagine you could shrink yourself down to the size of an atom and step inside. What you would see is chaos, thousands of tiny particles flying in every direction at incredible speed, bouncing off the walls, bouncing off each other, never stopping, never slowing down on their own. The box looks still from the outside. Inside, it is a storm. That storm is heat. Temperature is a measure of how fast those particles are moving. A cold room means the air molecules inside are moving slowly. A hot room means they are moving fast. When a thermometer reads 100 degrees Fahrenheit, what it is really telling you is the average speed of billions of invisible particles slamming into its glass tube. That is all temperature ever is, a speedometer for atoms. This idea is called the kinetic theory of matter, and once you understand it, heat stops being mysterious. You stop thinking of warmth as something added to an object, and start seeing it as a description of behavior. The atoms in a hot pan are vibrating so fast they transfer their speed to whatever touches them. That is what burning your hand on a stove actually is. Fast atoms hitting the atoms in your skin and speeding them up. Your nerves detect the change and send an alarm to your brain. Now think about ice. Ice feels cold because its water molecules are locked into a slow, rigid structure. When ice melts, heat energy from the surrounding air speeds up those molecules until they break free from the structure and start sliding past each other. That is liquid water. Heat them up more and they move so fast they escape the surface entirely. That is steam. Every change of state, solid to liquid, liquid to gas, is just a speed change. More energy means faster movement. Faster movement means the structure breaks down. It is not magic, it is statistics applied to trillions of invisible particles. Here is the number that puts it into perspective. The molecules in room temperature air are moving at roughly 1,000 miles per hour on average. You are surrounded at all times by invisible particles traveling at the speed of a supersonic jet. And that is what scientists call a moderate temperature. In the core of the sun, those particles move so fast the comparison breaks down entirely. The kinetic theory also explains something counterintuitive. When you pour boiling water into a cold cup, the water cools down and the cup warms up. The fast molecules in the hot water collide with the slow molecules in the cup and share their speed. The cup molecules speed up. The water molecules slow down. They eventually reach the same average speed, same temperature. The system balanced itself through collision. Energy moved. It transferred. It did not disappear. And that brings us to one of the most important rules in all of science, a rule that has never once been broken in any experiment ever recorded. Energy does not vanish. It changes form. It moves between objects, but the total amount stays exactly the same. Always. No exceptions. That rule is about to get tested in ways that the scientists who discovered it never imagined, because it holds perfectly in a lab, perfectly in a factory, perfectly on a planet. But at the scale of the entire universe, something deeply strange starts to happen. And that is where things get genuinely unsettling. Try to grab heat. You cannot. Try to hold a beam of light still in your palm. You cannot. Try to take the energy out of a moving car and put it in a box. You cannot. Energy is real. It does the most dramatic things in the universe, and you can never ever hold it by itself. This is one of the strangest facts in physics. Energy is always attached to something else. It lives inside objects. It moves between systems. But it never exists alone, floating free, waiting to be picked up. Every time you see energy, it is riding in a vehicle. Heat rides in the motion of atoms. Light rides in the movement of electromagnetic fields. Kinetic energy rides in the movement of mass. Pull the vehicle away, and the energy goes with it. Scientists call energy a property. A property is something that describes an object rather than something the object is made of. Color is a property. Velocity is a property. Temperature is a property. You would not say that a car is made of red. You say the car has the property of being red. Energy works the same way. Objects have energy. They are not made of it. This matters more than it sounds. For centuries, people imagined energy as a fluid or a substance, something you could bottle and sell. Even today, when someone says they feel full of energy, they picture it like a tank that fills and empties. The mental image is of a stuff, something with volume and weight. Take a rock and throw it off a cliff. The falling rock has kinetic energy, meaning energy of motion. When it hits the ground and stops, that energy has not disappeared. It has spread into heat in the ground, sound waves in the air, and tiny vibrations in the surrounding rock. You could, in theory, account for every single joule of that energy and find it somewhere else. But you could never find it floating alone, separated from matter or fields. It always has a home. The scientific definition of energy is the capacity to do work. Work means applying a force through a distance. Lift a box off the floor and you have done work on it. The box now sits higher and holds gravitational potential energy. It has the capacity to fall, which means it has the capacity to do work on whatever it lands on. The capacity is real even when the box is sitting still, completely motionless, apparently doing nothing. That hidden, stored capacity is what makes energy so strange. A tank of gasoline looks like an ordinary liquid. Boring, chemical, dense. But inside those molecules, billions of bonds are holding atoms together with tremendous force. Break those bonds and the energy releases explosively. The capacity was always there, invisible, locked inside the structure of matter. A single gallon of gasoline contains enough stored chemical energy to drag a 2-ton car forward for roughly 25 miles. All of that power hiding in a liquid that looks like dirty water. And here is the part that should make your head spin. If energy is just a property, just a description, does it even truly exist? Or is it simply a measuring tool humans invented to make the math work. Physicists and philosophers still fight over this. Some say energy is as real as anything in the universe. Others say it is a useful fiction, like the concept of average. Both sides have serious arguments. That debate is coming. But first, we need to understand the two great shapes energy takes before it gets complicated. And one of them is hiding in every moving thing around you. A school bus weighs about 14 tons. A bullet weighs about half an ounce. Put them side by side, and the bus seems infinitely more powerful. But send that bullet through the air at 2,000 miles per hour, and let the bus coast along at 3 miles per hour, and the bullet carries more energy. The bus does not stand a chance against the physics. This is kinetic energy, the energy of motion, and the rule that governs it is one of the most important in physics. Double the mass of a moving object, and you double its kinetic energy. Double its speed, and you quadruple its energy. Speed matters 4 times more than mass. That math is not obvious. It is also not negotiable. The speed-squared relationship is why car crashes at highway speed are so much more devastating than low-speed fender benders. A car traveling at 60 miles per hour carries 4 times the kinetic energy of the same car at 30 miles per hour. Engineers designing safety systems have to account for this. The crumple zones in a modern car are specifically designed to absorb and redirect kinetic energy before it reaches the people inside. Think about a Major League Baseball pitch. The ball weighs about 5 ounces. A fastball travels at roughly 100 miles per hour. A batter has less than 4/10 of a second to decide whether to swing. In that fraction of a second, the ball carries enough energy to leave a serious bruise through a catcher's mitt if caught wrong. The energy is entirely in the motion, and it releases the instant the ball stops. Now scale it up. A meteor the size of a school bus traveling through space at 50,000 miles per hour carries enough kinetic energy to flatten an entire city when it hits the ground. The rock itself is unremarkable. The speed turns it into a catastrophe. Here is something that feels wrong until you work through the physics. A feather dropped from shoulder height and a bowling ball dropped from shoulder height hit the ground at the same time if there is no air. Gravity accelerates both equally, but the bowling ball hits with thousands of times more kinetic energy than the feather. Same speed, completely different energy, because mass still matters alongside speed. Your own body has kinetic energy whenever you move. Walking at a normal pace gives you a small amount. Sprinting doubles your speed but quadruples your kinetic energy. This is why a sprinting football player is so much harder to tackle than a jogging one. The energy difference is not proportional to the speed difference. It is much larger. There is also a more personal version of this. A car accident at 15 miles per hour might leave you shaken. The same accident at 30 miles per hour is 4 times more energetic and 4 times more dangerous. Physics does not care about your feelings about that number. It just is what it is. But kinetic energy only covers objects in motion. What about objects sitting perfectly still that still somehow hold enormous power? A coiled spring, a drawn bow, a boulder on a ledge above a valley. Every one of those holds a type of energy just as real as any speeding bullet. It just waits patiently for the right moment to release. A rock on a cliff is doing nothing, sitting there, still, quiet, but put your hand under it and push it off the edge, and it will hit the ground with a force that could shatter pavement. Where did that force come from? The rock was not moving, it had no speed, and yet the power was real, waiting, loaded into the system like a weapon, with the safety on. That waiting power is potential energy, and it is everywhere. Potential energy is stored capacity. It lives inside a system that has been arranged in a way that can release energy when it changes. The rock on the cliff has potential energy because of its position. Gravity wants to pull it down. The height between the rock and the ground is the gap that holds the energy. Remove the ledge and gravity closes that gap instantly, converting the stored potential into motion. Gravitational potential energy is the most familiar kind. It is why dams work. Water held behind a dam sits high above a valley floor. Engineers route that water through tunnels, where its falling movement spins turbines and generates electricity. A mountain reservoir is essentially a giant battery made of water and gravity, and every second gravity is patient. It waits for the water to find a way down. But gravity is not the only way to store potential energy. A rubber band stretched between your fingers holds elastic potential energy. The molecules inside the rubber have been forced into an unnatural shape. They want to return to their resting state. When you release the band, that stored tension releases instantly as kinetic energy and heat. Snap it against your wrist, and you feel exactly how much energy a few inches of stretched rubber can hold. Springs work the same way. Compress a spring and the coils push back. Stretch it and the coils pull inward. Either way, the structure stores energy. A wound clock spring could run a watch for a full day before releasing all its stored energy. Every tick is a tiny piece of that potential escaping in a controlled, measured way. Chemical potential energy is the strangest and most powerful version. The food you eat holds this kind of energy inside the molecular bonds connecting its atoms. Your digestive system breaks those bonds and releases the energy. Your body captures it, uses some of it for movement, some of it for heat, and stores the rest as fat, which is just another form of chemical potential energy on standby. A peanut butter sandwich holds enough chemical potential energy to power a person walking for about 45 minutes. That energy is invisible, locked inside molecular structures doing nothing until your body breaks it apart. Here is what connects all forms of potential energy. They are all about position or arrangement. How high is the rock? How stretched is the rubber band? How tightly bonded are the atoms? The energy sits in the gap between the current state and the natural resting state. Physics describes this as a system under tension with a preferred configuration it has been denied. Potential energy transforms into kinetic energy every time a system is allowed to move toward that preferred state. And the reverse is also true. You do work on a system and you add potential energy to it. Lift a weight, compress a spring, charge a battery. You are doing work and storing it. And in 1905, one scientist looked at mass itself and realized it was just another form of stored energy. What he found rewrote everything. In 1905, Albert Einstein was 26 years old and working as a patent clerk in Switzerland. He had no lab, no team, no major research position. What he had was an extraordinary ability to picture physical scenarios in his mind and follow the logic wherever it led. That year he published 4 papers. Any single one of them would have made him famous. Together, they changed physics permanently. One of those papers contained 3 letters and a number that may be the most recognized arrangement of symbols in all of human history. Energy equals mass times the speed of light, squared, compact, simple-looking, and completely world-shattering. What Einstein showed was that mass and energy are the same thing. They are not similar. They are not related. They are the same thing expressed in 2 different ways. Mass is a form of stored energy, condensed into matter. Energy is mass that has been freed from a physical form. The speed of light is roughly 186,000 miles per second. Squared, that number becomes enormous. The equation says that even a tiny amount of mass contains a breathtaking amount of energy. 1 pound of any matter, if you could convert it entirely into pure energy, would release roughly 10 billion kilowatt-hours of power. That is enough to supply electricity to the entire United States for several days. This was not just an abstract idea. It had immediate consequences. It explained why the sun produces so much energy. The sun burns through about 4 million tons of mass every single second, converting that mass directly into energy through nuclear fusion. That is where sunlight comes from. The sun is slowly shrinking as its mass turns into the light and heat that cross 93 million miles of space to warm your skin. Einstein's equation also predicted that energy, not just matter, has mass. If mass is energy, then energy must have mass too. That prediction has been confirmed in precise experiments. A compressed spring actually weighs slightly more than a relaxed spring, because the stored elastic energy adds a tiny, measurable amount of mass. The difference is far too small to detect on a bathroom scale, but instruments sensitive enough to measure it confirm it every time. This symmetry is one of the most beautiful ideas in all of science. Matter and energy are interchangeable. The universe keeps a single account, not two separate ones. Mass deposits energy into the account. Energy withdraws it. The total never changes. But the equation opened a disturbing door. If even a small amount of mass holds that much energy, then releasing it intentionally becomes possible. Nuclear weapons are the direct application of Einstein's equation. Splitting a uranium atom releases a fraction of its mass as energy. Do it to enough atoms at once, and the result flattens a city. Einstein himself understood this. He spent years afterward advocating against the weapons his equation helped make possible. The equation also left a question open. If mass and energy are the same thing, and energy has no physical substance, does matter actually have physical substance either? Is a rock just energy locked into a slow, stable form? Physics says yes, and that answer gets stranger the deeper you go. Because light, which clearly carries energy, carries none of the mass. Zero. And yet it flies through the universe delivering real measurable power. That paradox took Einstein's own ideas and stretched them to a breaking point. Pick up a paperclip. It weighs about 1 gram, about the same as a small paper bill folded in half. It sits on your desk doing nothing. Absolutely unremarkable. And according to physics, if you could convert every atom of that paperclip into pure energy, you would release an explosion roughly equivalent to the atomic bomb dropped on Hiroshima. 1 gram of matter, one of the most destructive events in human history. Same energy. This is the number that makes physicists go quiet when they think too hard about it. Einstein's equation says that mass times the speed of light squared equals energy. The speed of light squared is such an enormous multiplier that even the tiniest mass translates into a staggering amount of energy. That 1 gram paperclip holds about 90 trillion joules of energy if fully converted. 90 trillion. That is roughly the amount of energy the entire United States uses in about half a day. The reason the world has not been vaporized is that converting matter into pure energy is extraordinarily difficult. Nature does not allow it easily. The atoms in a paperclip are locked into structures that resist being dismantled. Even in a nuclear bomb, only about 0.1% of the total mass converts into energy. That tiny fraction is enough to devastate a city. The rest of the mass stays as matter. If even full conversion were possible, 1 gram of anything would do it, not uranium specifically. Not some exotic material, a gram of water, a gram of air, a gram of your fingernail. The substance does not matter because mass is mass, and all mass stores energy at the same ratio. Stars do something closer to full conversion over long timescales. Through nuclear fusion in their cores, they steadily convert a fraction of their mass into energy. Our Sun has been doing this for about 4.5 billion years, and still has enough mass to keep going for another 5 billion. The total output is so vast that the Sun sheds about 4 million tons of itself every second as pure radiated energy, and it barely notices. Here is the version of this that should make you genuinely unsettled. Particle accelerators, the massive machines scientists use to study subatomic physics, can smash particles together with enough energy to convert them entirely into pure energy, which then instantly reassembles into brand new particles that never existed before. Mass becomes energy. Energy becomes new mass. The identity of matter is temporary. A proton fired through a particle accelerator and smashed into another proton does not just break apart into smaller pieces. It can produce new particles from the raw energy of the collision, particles that did not exist a moment before, created from nothing but kinetic energy. This happens millions of times per second in laboratories right now. What Einstein's equation really says is that the border between matter and energy is a border humans drew on a map, and the universe ignores it entirely. Matter and energy are one thing, two phases of the same underlying reality. And then there is light. Light carries real energy. You can feel it as warmth on your face. Solar panels convert it into electricity. Radiation from the sun causes sunburns. But light has no mass. Zero. If matter and energy are the same thing, how does light carry energy without any mass? That question tore a hole in the logic, and the answer changed physics again. In the early 1900s, physicists thought they had a clean picture of the world. Matter was matter. Energy was energy. They could convert into each other, thanks to Einstein, but both were well defined. Then someone looked at light too carefully, and the whole picture developed a crack that has never fully closed. Light is made of particles called photons. This was confirmed through decades of careful experiments. You can count individual photons. You can send them one at a time through an experiment. They arrive like tiny, discrete packets of something, not a smooth, continuous wave. But photons have exactly zero mass. You cannot weigh a photon. You cannot slow one down by adding gravity. They travel at the speed of light because they are light, and a particle with zero mass can only exist at the speed of light. Stop a photon and it ceases to exist. It gets absorbed. So here is the problem. Energy and mass are supposedly the same thing. Einstein showed this, but photons have energy and zero mass. If you plug zero mass into Einstein's equation, you get zero energy. But photons clearly carry energy. Hold your hand in sunlight. You feel the warmth. That warmth came from photons. Where is the contradiction? The answer required an extension of Einstein's original equation. The full version includes a term for momentum. Photons carry momentum even without mass. This sounds impossible, but momentum can come from motion alone in the world of quantum mechanics. A photon moving at the speed of light carries momentum based purely on its frequency, meaning how fast it oscillates. Higher frequency means higher energy. This is why ultraviolet light causes sunburns, and visible light does not. Ultraviolet photons oscillate faster. They carry more energy. When they hit cells in your skin, they carry enough energy to damage the molecular bonds inside your DNA. Visible light photons do not carry enough energy to do that. Same speed, very different energy. The difference lives entirely in the frequency. This is also how solar panels work. A photon strikes a silicon crystal in a solar panel. The photon's energy kicks an electron loose from its atom. That freed electron starts moving through a circuit. Movement of electrons is electricity. A massless particle carrying momentum energy causes matter to move. That is how you power a city with sunlight. The existence of massless particles with energy forced physicists to completely rethink what energy actually is. If it does not require mass, it cannot simply be a form of matter. Energy is something more fundamental, something that can exist in the pure behavior of a field, without needing a physical object to carry it. And that idea that energy lives in fields rather than particles eventually grew into the most precise theory in all of science. A theory that predicts the behavior of particles to a level of accuracy that no other scientific model in history has matched. But before we get there, we need to talk about a rule so absolute, so unbreakable that every technology ever built depends on it. A rule that says energy can shapeshift into anything, take any form, travel anywhere, but it can never, under any circumstances, disappear. In the Mojave Desert, rows of solar panels stretch across the sand for miles, angled precisely toward the sun. Every second, an invisible storm of massless particles is traveling 93 million miles across empty space, hitting those panels and producing enough electricity to power hundreds of thousands of homes. No fuel, No combustion, no moving parts, just the momentum of light. Understanding how that actually works requires going inside a solar panel at the atomic scale. Silicon atoms hold their electrons in a way that makes them almost but not quite free. The electrons are bound to their atoms but loosely enough that the right push can knock them loose. That push comes from photons. When a photon arrives from the sun, it travels through the top layer of the solar panel and hits a silicon atom. If the photon carries enough energy, which depends entirely on its frequency, it transfers that energy to one of the outer electrons in the atom. The electron absorbs the energy, breaks free from its atom, and starts moving. A free moving electron is an electric current. Route those electrons through a wire, and you have electricity. The elegance of this process is staggering. A particle with no mass, moving at the fastest speed physically possible, crosses nearly 100 million miles of empty space, arrives at a thin slice of treated silicon, and its pure motion energy lifts an electron out of its atom and pushes it into a circuit. No heat engine, no turbine, no burning fuel. Just light and matter interacting at the quantum level. This process is called the photoelectric effect. Einstein actually won his Nobel Prize for explaining it, not for the theory of relativity, which surprises most people. The photoelectric effect proved that light delivers energy in discrete packets. Each photon delivers a fixed amount, depending on its frequency. Below a certain frequency, no photons can dislodge electrons, regardless of how bright the light is. Above that frequency, even dim light can do it. The energy comes in chunks, not in a continuous stream. That discovery was the beginning of quantum mechanics. It forced physicists to abandon the idea that energy flows like water. Energy comes in specific minimum units like coins rather than liquid. You cannot have half a coin. You cannot have half a photon's worth of energy delivery. The universe trades in precise denominations. On a practical level, this is why solar panels have real limits. A photon below the threshold frequency passes through the silicon without interacting. A photon above the threshold does the job. Engineers work to build materials that respond to a wider range of photon frequencies, capturing more of the sun's output. A standard silicon panel converts roughly 20% of sunlight into electricity. The other 80% passes through or becomes heat. 20% sounds inefficient, but consider what is happening. The sun fuses hydrogen atoms in its core, converting mass into energy. That energy travels across 93 million miles as massless photons. Those photons arrive at a thin sheet of treated glass and sand, and 1 in 5 transfers its energy directly into flowing electrons, all without a single moving mechanical part. The energy chain from the sun's core to your phone's charging cable is one of the most extraordinary sequences in nature. And it all works because of a law so fundamental that breaking it would mean the universe itself would stop making sense. In the mid-1800s, a German physicist named Julius von Meyer was on a ship sailing to Indonesia as a medical officer when he noticed something strange about the blood he was drawing from patients. In the tropics, where it was hotter outside, the blood from the veins looked nearly as bright red as arterial blood. In Europe, venous blood looked much darker. This bothered him. He knew that the color difference had to do with how much oxygen the blood was carrying. But why would tropical patients burn less oxygen? Then it hit him. In a hot climate, the body does not need to burn as much fuel to maintain its temperature. It does less thermal work. The body uses energy for heat and for motion. And in the tropics, less went to heat, so more stayed in the blood as unused oxygen. From that observation on a ship, Mayer developed one of the most powerful ideas in physics. He argued that heat, motion, and work are all forms of the same thing, and that thing, energy, can change its form but can never be created or destroyed. The total amount in an isolated system stays exactly constant. This is the first law of thermodynamics, and it has never been violated in any experiment, in any lab, in any natural process ever recorded. Follow the energy in anything, and it always adds up. A lit candle releases chemical energy stored in the wax. That energy becomes heat and light. The heat warms the air above it, which rises and creates a tiny breeze. The light bounces around the room, warming walls, furniture, and eventually turning into heat. Every single joule of energy that started in that wax ends up somewhere trackable. The wax does not run out of energy that vanishes. It transforms every bit into something measurable. The human body does this constantly. The food you eat holds chemical potential energy in molecular bonds. Your digestive system breaks those bonds. About 40% of that released energy powers your muscles, your heartbeat, your thinking. The other 60% becomes body heat. Put a person in a sealed, insulated room and measure the heat they produce over a day, then compare it to the chemical energy in the food they ate. The numbers match precisely. The body is an energy converter, not an energy creator. This matters enormously for technology. Every engine, power plant, and battery ever built was designed with the first law as its foundation. Engineers do not try to get more energy out than they put in. Physics forbids it. Instead, they try to minimize the energy lost to unwanted forms, mainly heat, and maximize the energy converted into useful work. The efficiency of a car engine is a direct expression of this. A typical gasoline engine converts about 30% of the chemical energy in fuel into motion. The other 70% becomes heat from friction, exhaust, and the combustion process itself. That heat escapes into the air. It is gone from the car system. It did not disappear from the universe. It just spread out into the environment, too scattered to collect again. The first law is reliable. It is absolute. And it hides something deeply strange. If energy is always conserved, always present, always transforming, then where exactly is it going in a universe that is getting colder and more spread out every second? That question leads to the second law of thermodynamics, which explains why energy, even though it never disappears, slowly becomes useless. But before that, watch what happens when a single coffee cup falls off a counter. You set a full coffee mug on the edge of a table. Someone bumps it. It slides off the edge and falls to the floor. In 3 seconds, you witness one of the most complete demonstrations of energy transformation physics has to offer. Every form of energy makes an appearance. Nothing is wasted. Everything goes somewhere. Start at the beginning. Before the mug moves, it holds gravitational potential energy. It is elevated above the floor, and gravity wants to close that gap. The amount of potential energy it holds depends on 2 things: its mass and its height above the floor. A mug sitting 3 feet up holds roughly the same gravitational potential as any object of equal mass at that height. The moment the mug slides off the edge, the transformation begins. Potential energy starts converting into kinetic energy. As the mug drops, it speeds up. The higher the drop, the faster it goes when it arrives. Every inch of falling trades stored positional energy for speed. By the time it is 1 inch from the floor, nearly all the potential energy has become motion. Then it hits. The impact converts kinetic energy into several things simultaneously. Some become sound. The crash you hear is a pressure wave moving through the air carrying energy outward in all directions. Some becomes heat. The collision forces atoms in the mug and the floor to slam into each other violently, speeding up their vibrations. The temperature at the point of impact rises slightly. Some energy goes into deforming the ceramic, cracking it, shattering it. The work of breaking chemical bonds in the ceramic absorbs energy. And if the coffee splashes, the liquid carries kinetic energy as it sprays outward. Droplets hit the wall, converting their motion into heat and the sound of tiny impacts. The coffee eventually settles, and its temperature gradually equalizes with the room, spreading its thermal energy into the surrounding air and floor. Every joule of energy that was stored in the gravitational potential of the mug on the table has now become sound, heat, and broken bonds. Nothing vanished. Physics kept perfect accounting the entire time. Here is what you cannot undo. You could pick up all the ceramic pieces, glue the mug back together, replace the coffee, and set it back on the table. But you cannot recollect the heat that spread through the floor and air. You cannot reassemble the sound wave. You cannot unscatter the thermal energy. The first law says energy is conserved. The second law says the direction of transformation matters. Energy spreads out, and that process does not reverse itself. The coffee mug breaking is not just a story about energy conservation. It is a story about energy quality. Concentrated energy, like a mug held high above the floor, can do useful work. Spread out energy, like warmth distributed across a floor, cannot. The universe constantly moves energy from concentrated to spread out, from useful to unusable, from ordered to disordered. Physicists call this increase of disorder entropy, and the universe's tendency to maximize entropy is why everything eventually breaks down, cools down, and spreads out. But not all energy starts this way. Some energy is hidden so deep inside matter that you need extreme conditions to release it. The energy hiding inside the bonds between atoms is so concentrated, it powered civilization for a century, and the way it gets released is both beautiful and terrifying. Inside every molecule you have ever seen, atoms are holding on to each other with a grip that took billions of years of chemistry to develop. That grip is an electromagnetic force. Electrons shared between atoms create a bond. The bond holds the atoms in a fixed arrangement, and inside that arrangement, energy is stored like a spring under tension. Chemical potential energy lives in those bonds, every single one of them. A water molecule holds its hydrogen and oxygen atoms together with bonds that contain a precise amount of stored energy. A glucose molecule, the sugar your brain runs on, holds its 12 carbon atoms in a ring structure packed with chemical energy. A gasoline molecule holds even more. The process of chemistry is the process of rearranging these bonds, break old bonds, and form new ones. Every time a bond breaks, energy releases. Every time a new bond forms, energy is absorbed or released, depending on which arrangement is more stable. When you eat food, your body is running a controlled chemistry operation. Your digestive system breaks apart the molecular bonds in carbohydrates, fats, and proteins. As those bonds break, energy releases. Your cells capture that energy and use it to build a molecule called adenosine triphosphate, which is essentially your body's energy currency. Your muscles spend that currency to contract. Your brain spends it to fire neurons. Your kidneys spend it to filter blood. The calorie count on food packaging is a measurement of chemical potential energy. One food calorie, the kind printed on nutrition labels, equals roughly 4,000 joules of energy. A standard chocolate bar holds about 250 food calories, meaning about 1 million joules of chemical energy locked into its molecular bonds. Your body can only extract and use a portion of that efficiently, but the potential is enormous. Gasoline is a hydrocarbon molecule, meaning chains of hydrogen and carbon atoms held together by strong bonds. When gasoline burns in a car engine, those bonds break apart violently. The carbon atoms grab oxygen from the air and form carbon dioxide. The hydrogen atoms grab oxygen and form water. Both of those new bonds release energy, and the new bonds are more stable than the old ones. The energy difference between the old arrangement and the new one comes out as heat and expanding gas. That expanding gas pushes pistons. The pistons turn a crankshaft. The crankshaft turns the wheels. Explosives work on the same chemistry but faster. TNT holds its molecular structure in an arrangement that is desperate to rearrange itself into something more stable. Given a trigger, the rearrangement happens across trillions of molecules simultaneously in microseconds. The energy release is so fast that the surrounding air cannot move out of the way quickly enough. The result is a shock wave. An explosion is simply extremely fast chemistry. Every fire you have ever seen is chemistry. Every breath you take is chemistry. The warmth of the sun reaching Earth involves chemistry in the leaves that capture it. The energy hiding in chemical bonds powers the entire surface of this planet. But there is another kind of bond, far stronger than chemical bonds, a bond that holds the nucleus of every atom together. The energy inside those bonds makes chemical energy look like a candle next to a supernova, and releasing it changed the world forever. Somewhere over the Great Plains, a thunderstorm the size of a small state is building. Inside the clouds, ice crystals are colliding with heavier Graupel pellets, which are soft hailstones. Every collision strips electrons from one particle and deposits them onto another. The lighter ice crystals, now carrying extra electrons, get swept to the top of the cloud by updrafts. The heavier Graupel sinks to the bottom. After about 20 minutes of this, the top of the cloud carries a massive positive charge and the bottom carries a massive negative charge. The charge difference between top and bottom can reach hundreds of millions of volts. And then the bottom of the cloud starts inducing a charge in the ground below it. The negative charge at the cloud's base repels electrons in the ground outward, leaving the ground surface temporarily positive. Now you have a giant negative charge hovering above a giant positive charge, separated by about a mile of air. Air is normally a poor conductor of electricity, but at high enough voltage, it stops being a good insulator. The electric field between the cloud and the ground becomes so intense that it begins tearing electrons off air molecules, creating a channel of ionized gas that conducts electricity. This channel, called a stepped leader, grows downward from the cloud in invisible steps. Meanwhile, from tall objects on the ground like trees and buildings, positive charges reach upward in their own channels called streamers. The moment a downward leader meets an upward streamer, the circuit completes. Billions of electrons pour from the cloud into the ground along that ionized channel in about 200 microseconds. That surge of electrons is lightning. The channel heats to roughly 50,000 degrees Fahrenheit, which is nearly 5 times hotter than the surface of the sun. The superheated air expands explosively. That expansion is thunder. A single lightning bolt carries about 5 billion joules of energy. That sounds enormous, enough to power a home for a month, but the bolt delivers that energy in about 200 microseconds. All 5 billion joules in a fraction of a second. The power of a single lightning strike, measured in watts during that instant, is roughly 1 trillion watts. For comparison, the entire electrical generation capacity of the United States is about 1 trillion watts sustained. The problem with lightning as an energy source is the duration. All that power lasts less than the blink of an eye. You cannot store it fast enough. You cannot capture it reliably enough. Nature produces a spectacular display, and then it is gone. Electrical energy in the form humans use it is far more controlled. Power plants generate a steady, controlled flow of electrons through wires. The electrons do not travel from the power plant to your home. They oscillate back and forth 60 times per second, and this vibration carries energy along the wire, like a wave carries motion across water. Every appliance you plug in extracts energy from that oscillation and converts it into heat, light, sound, or motion depending on what the device does. The wire itself loses a small amount of energy to heat as electrons push through the metal. That is why power lines get warm. Electrical energy is the most versatile form of energy humans have ever harnessed. It can become any other form almost instantly, and the technology built around moving electrons has reshaped civilization faster than any other force in history. But electrical energy, chemical energy, gravitational energy, all of it represents the behavior of matter. Remove the matter, and you might expect energy to disappear. Something discovered in a lab in the 1950s proved that idea completely wrong, and it suggested the empty vacuum of space is anything but empty. Inside the nucleus of every atom, protons and neutrons are packed together in a space roughly 100,000 times smaller than the atom itself. If an atom were the size of a football stadium, the nucleus would be a marble at the center, and inside that marble, forces are operating at a scale that dwarfs everything in chemistry. The protons inside a nucleus all carry positive electrical charges. Positive charges repel each other. The closer they are, the harder they push apart. Pack dozens of protons into a space the size of a marble, and the repulsive force between them is almost unimaginably intense. Something has to be holding them together against that force. Otherwise, every atomic nucleus would explode instantly. That something is called the strong nuclear force. It is the most powerful force in nature. It only operates at extremely short distances, shorter than the width of a single proton, but within that range, it overwhelms the electromagnetic repulsion and locks protons and neutrons together into a stable nucleus. The energy stored in that lock is called binding energy, and it is the most concentrated form of energy found anywhere in nature. Chemical bonds, the ones holding molecules together, involve the electrons on the outside of atoms interacting with each other. The energies involved are measured in a handful of electron volts. Nuclear binding energies are measured in millions of electron volts. One nuclear reaction releases roughly 1,000,000 times more energy than one chemical reaction. This is why uranium can power a city. A uranium fuel pellet roughly the size of a fingertip holds as much energy as 17,000 cubic feet of natural gas. The difference is entirely in the binding energy of the nucleus versus the bond energy of molecules. Fission is the process of splitting heavy atomic nuclei. Fire a neutron at a uranium nucleus, and under the right conditions, it absorbs the neutron and becomes unstable. The nucleus wobbles, stretches, and splits into two smaller nuclei. Those smaller nuclei are more tightly bound than the original, meaning they sit at a lower energy state. The difference in binding energy releases as gamma radiation and the kinetic energy of the fragments. Two split nuclei have less total mass than the original uranium atom. That missing mass became energy, exactly as Einstein predicted. The fragments fly outward and collide with neighboring atoms, producing heat. A nuclear reactor controls this chain of events, using the heat to boil water, which turns turbines which generate electricity. A nuclear bomb removes the controls and lets the chain reaction run unchecked. Fusion is the other direction. Force two light nuclei like hydrogen together until the strong force grabs them and merges them into a heavier nucleus. The product is more tightly bound than the two originals. Again, the difference in binding energy releases. The sun runs on fusion. Every second, the sun converts about 600 million tons of hydrogen into about 596 million tons of helium. The missing 4 million tons becomes pure energy. That is where every photon of sunlight comes from. Nuclear energy shows that matter itself is a form of stored power. The universe locked an enormous amount of energy into the structure of atoms when it created them. We are learning slowly to unlock it. And while nuclear energy sits inside matter, there is another kind of energy that scientists once assumed was completely absent from empty space. Something strange and deeply confusing was discovered inside a vacuum chamber decades ago, and it proved that the universe stores energy even where nothing exists. Clap your hands together right now. The impact forces air molecules outward in all directions. Those molecules slam into the ones next to them. Those hit the ones beyond them. A chain reaction of collisions moves outward from your hands at about 760 miles per hour. When those collisions reach your eardrums vibrate at the same rate. Your auditory nerve translates that vibration into an electrical signal. Your brain decodes it as sound. That entire process, from your hands clapping to your brain hearing it, takes less than 3 milliseconds in a small room. Sound is a pressure wave. It is energy moving through matter by pushing particles together and pulling them apart in a repeating pattern. The wave does not carry the particles with it. The air molecules do not travel from your hands to your ears. They push their neighbors, which push their neighbors, passing the disturbance along like a crowd doing a wave in a stadium. The energy moves. The matter stays roughly in place. The frequency of the wave determines the pitch. Fast oscillations produce high-pitched sounds. Slow oscillations produce low-pitched ones. The human ear can detect frequencies ranging from about 20 oscillations per second up to 20,000. Below 20, you feel it as vibration. Above 20,000, you cannot perceive it at all, though many animals can. The amplitude of the wave determines the volume. Bigger pressure swings mean louder sound. Sound intensity is measured in decibels, and the scale is logarithmic. An increase of 10 decibels means 10 times the physical intensity. A normal conversation sits around 60 decibels. A rock concert peaks around 120 decibels. That concert is not twice as intense as a conversation. It is 1,000,000 times as intense. At very high intensities, sound stops being just noise and starts being physically destructive. A sound at around 190 decibels is powerful enough to cause air pressure swings large enough to tear apart lung tissue. The physics here is simple. A sufficiently large pressure wave compresses the air in your lungs faster than the tissue can flex, and the alveoli, the tiny air sacs in your lungs, rupture. Military and law enforcement have used this in directed sound weapons. Acoustic devices that project highly focused beams of intense sound can cause severe pain, disorientation, nausea, and in extreme cases, organ damage at ranges of several hundred yards. The energy is carried purely by air pressure, and it interacts directly with the body at the cellular level. The same principle works on smaller scales inside medical ultrasound machines, which use high-frequency sound waves above the range of human hearing to image soft tissues inside the body. The sound waves bounce off different tissues at different rates, and the returning signals are processed into images. The same wave technology used to destroy things can also see through them, depending entirely on the intensity and frequency. Sound also travels dramatically faster through denser materials, through air about 760 miles per hour, through water almost 4 times faster, through steel about 15 times faster than through air. The energy transfers more efficiently when molecules are packed closer together. And here is the concept that connects sound to everything we have discussed so far. Sound is energy with a physical carrier. Remove the matter, remove the air or water or steel, and sound cannot exist. There is no sound in space because there are no particles to carry the pressure wave. But as it turns out, something even stranger can carry energy without matter at all. And what physicists discovered about the nature of that carrier changed the entire foundation of how we understand what matter, energy, and space itself actually are. Put your hand flat on a table. It feels solid, dense, immovable, but the atoms making up your hand and the atoms making up the table are almost entirely empty space. The nucleus of an atom occupies a fraction so small compared to the atom's total size that the comparison breaks understanding. If a hydrogen atom were expanded to the size of a football stadium, its nucleus would be a marble at the 50-yard line. Everything else would be empty. So why does your hand not pass through the table? Because empty space is not actually empty. The space inside and around atoms is filled with invisible fields. These fields extend throughout all of space. They vibrate, they interact, they carry energy, and according to modern physics, they're the most fundamental thing that exists. Everything else, every particle, every force, every bit of matter in the universe, is a ripple in one of these fields. This framework is called quantum field theory, and it is the most precisely tested theory in the history of science. Its predictions match experiments to an accuracy that physicists describe as equivalent to measuring the distance from New York to Los Angeles and being off by less than the width of a single human hair. There is an electron field that fills all of space. When the field vibrates in a concentrated way, that vibration appears as an electron. There is a quark field. Vibrations in the quark field are quarks. There is a photon field called the electromagnetic field. Vibrations in that field are photons. Every fundamental particle you have ever heard of is a ripple in its corresponding field. It is made of excited regions of invisible fields. The solidity you feel when you touch a table comes from the electromagnetic fields of your hand's atoms, interacting with the electromagnetic fields of the table's atoms. The fields push against each other. You feel that push as resistance. Solid matter is just fields refusing to overlap. Energy in this picture is what fields carry when they vibrate. A calm field has low energy. An excited field, meaning one with a strong vibration, has high energy. When a photon travels through space, it is the electromagnetic field vibrating at a specific frequency as that vibration moves from one location to another. The energy is in the wave itself. This answers the old question about whether energy needs matter to exist. In quantum field theory, the fields come first. Matter is a secondary phenomenon, a type of field behavior. Energy is the property of the field's activity. You do not need matter for energy. You need fields, and fields are everywhere and unavoidable. The table that feels so solid is mostly fields interacting. Your body is fields. The light crossing the room is a field in motion. The air between objects is filled with quantum fields at various levels of activity. Pull everything out, every particle, every vibration, and you still have the fields. And those fields, even in their lowest possible state, still contain energy. That is not a theory. It is a measured fact. And the experiment that proved it involves two metal plates, a tiny gap, and a force that should not exist. What happens between those plates has been confirmed in laboratories around the world, and what it implies about the nature of empty space changes every assumption about where energy comes from. Imagine the surface of a lake. When the water is still, the lake holds a baseline amount of energy, mostly just the thermal motion of water molecules. Throw a stone in, and you create a ripple. The ripple moves outward. It carries energy from the impact point to the shore. The water molecules themselves do not travel to the shore. The pattern of disturbance does. The energy rides the pattern. Quantum fields work in almost exactly the same way, except the fields are not made of water or anything physical. They are mathematical structures embedded in space itself, and their ripples are the particles of reality. An electron is a specific kind of ripple in the electron field. It has a fixed mass, a fixed charge, and a fixed spin, because those are properties of that particular field. Every electron in the universe is identical to every other electron because they are all the same type of ripple in the same field. There is no variation. A ripple in the electron field always produces an electron, every single time. Energy is what determines the size of the ripple. A low-energy electron is a small disturbance in the electron field. A high-energy electron is a more intense disturbance. Give an electron more energy, and the ripple grows. Take energy away, and it shrinks. If you could drain all the energy from an electron's ripple, the electron would cease to exist. The field would return to its ground state. This means particles are temporary. They are not permanent features of the universe. They are excitations, and excitations require energy to maintain. The particle exists as long as the field vibration persists. When the energy disperses, the particle dissolves back into the background field. This sounds abstract, but it has direct consequences you have already seen. When a particle accelerator smashes protons together, the kinetic energy of the collision excites the surrounding quantum fields so intensely that new ripples form. New particles emerge from the energy of the impact. The fields take the energy input and express it as matter. This is why particle collisions create particles that were never present in the original beam. They came from the fields. The energy does not create particles from nothing. The energy was always there in the kinetic motion of the colliding protons. What changes is the form. Kinetic energy converts into field excitation. Field excitation appears as new particles. Matter is born from energy, exactly as Einstein's equation predicted, but now with a mechanism. The fields. Photons are the clearest example. A photon is a ripple in the electromagnetic field. with no mass excitation. It is pure field energy in motion. When a photon is absorbed by an electron, the photon's ripple disappears and the electron's ripple intensifies. The energy moved from one field excitation to another. The photon ceased to exist. The electron became more energetic. The total energy stayed constant. This constant reshuffling of energy between field excitations is what every physical process in the universe actually is at the deepest level. Chemical reactions, nuclear fission, light traveling across the cosmos, your brain processing a thought, all of it is quantum fields exchanging energy by creating and destroying excitations. And here is where it gets stranger. Even in a perfect vacuum, with zero particles, with every ripple smoothed out, the fields do not go quiet. They cannot. The universe forbids it. And the proof of that prohibition was measured in a laboratory with two metal plates in a gap smaller than the width of a human hair. In 1948, a Dutch physicist named Hendrik Casimir made a prediction that sounded ridiculous. Take two flat metal plates, place them facing each other in a perfect vacuum with no air between them, no light, no particles of any kind. Separate them by a distance smaller than a grain of sand. And then, he predicted, those plates would be pushed together by a force coming from absolutely nothing. Nobody took a measurement delicate enough to confirm it. Until 1997, the force was real. The empty space between those plates was pushing them together. Here is why. Quantum fields cannot be completely still. This is a rule enforced by one of the most important principles in physics, the Heisenberg uncertainty principle. You cannot know both the exact energy of a field at a point and the exact rate at which it is changing at that point simultaneously. If a field were truly perfectly at zero energy, you would know both things exactly. The universe forbids that. So the fields always fluctuate. They jitter. They briefly spike to higher energy and drop back down. Constantly, everywhere, even in a vacuum. These fluctuations create virtual particles. Pairs of particles pop into existence for a fraction of a second and then annihilate each other before they can be directly detected. This happens continuously throughout all of space. The vacuum is not empty. It is a churning sea of temporary particle pairs constantly appearing and disappearing. Now bring in the two plates. Between the plates, only certain wavelengths of field fluctuation can fit. The space is too small for large wavelengths. Think of it like a guitar string. A string has a fixed length and only specific vibrations fit on it. Between the Casimir plates, only certain vacuum fluctuations are allowed. Outside the plates, all wavelengths are allowed, so the vacuum energy outside the plates is greater than the vacuum energy between them. That imbalance creates a net force pushing the plates inward. The force is small, but it is measurable, and it is real. This is not a theoretical curiosity. The Casimir effect has been measured with increasing precision over the past 3 decades and matches predictions extremely well. It has direct engineering consequences. At the scale of nanometers, where tiny machines operate, the Casimir force is significant. Designers of microscale devices must account for it, or their machines stick together unexpectedly. What the Casimir effect tells us is that space itself has a baseline energy. The vacuum is not a passive container for matter and energy. It is an active participant. Even after you remove every particle, every photon, every field excitation, space still buzzes with quantum activity. The ground state of quantum fields is energetic, not empty. The total amount of vacuum energy in the universe may be enormous. Estimates based on quantum field theory suggest that empty space contains more energy per cubic inch than the most energetic nuclear reactions. If true, this energy is everywhere, in every corner of the universe, and we have no mechanism to access or extract it. This vacuum energy may also be connected to one of the greatest unsolved mysteries in all of science, a force that is doing something to the entire universe right now. something that physicists discovered only about 30 years ago and that no current theory can adequately explain. In the space between your fingers right now, something extraordinary is happening. Pairs of particles are appearing from the vacuum and disappearing again before any instrument can directly catch them in the act. An electron and its antimatter twin, a positron, flicker into existence together. A photon borrows energy from the vacuum and returns it. Quarks and antiquarks materialize and vanish in intervals so brief they are measured in millionths of a billionth of a second. These are virtual particles, and they are real enough to change the measurable properties of actual matter. The uncertainty principle is the permission slip for this behavior. It says that the more precisely you measure the energy of a system during a very short time interval, the less you know about that energy's exact value. At short enough timescales, energy is genuinely uncertain. The vacuum can borrow a burst of energy, use it to create a particle pair, and return it before the loan shows up on any ledger. The shorter the borrowing period, the more energy can be borrowed. This sounds like the universe cheating, and in a sense it is. But the debt is always repaid. Virtual particles cannot exist for long. The more massive the particle pair, the faster they must annihilate. A virtual electron-positron pair lasts about 10 times longer than a virtual quark-antiquark pair because quarks are heavier and the energy debt is larger. Every pair vanishes before it can travel any meaningful distance. Despite their invisibility, virtual particles leave fingerprints on real physics. One of the most precise measurements in all of science involves an electron sitting in a magnetic field. The electron behaves slightly differently from what you would predict if the vacuum were truly empty. The difference is tiny but measurable. It comes from the electron constantly interacting with virtual photons, flickering in and out of the vacuum around it. When physicists calculate the electron's behavior, accounting for all these virtual interactions, the prediction matches the measured value to better than 10 decimal places. The virtual particles are doing something real. The same logic applies to nuclear forces. Protons and neutrons inside an atomic nucleus exchange virtual particles called pions at high speed. These exchanges are what transmit the residual nuclear force that holds nuclei together. The force that keeps atomic nuclei from flying apart comes from particles that technically do not exist in any permanent sense. This is deeply strange. The forces of nature are mediated by particles that only exist on loan from the vacuum. The electromagnetic force between two electrons is caused by virtual photons passing between them. Neither electron ever touches the other. They communicate through temporary messengers that cease to exist the moment they finish their job. Now, zoom out. The vacuum is not a region of nothing. It is a region of everything potential. Every possible particle type is constantly attempting to exist, flickering at the edges of reality, constrained only by the energy budget and the uncertainty window the universe allows. And this connects to a discovery that changed cosmology completely. If virtual particles carry energy, and if that energy is real enough to push metal plates together and shift the behavior of electrons, then the vacuum has a genuine energy density. And something with energy density has gravitational effects. The vacuum of space should be pulling on itself and on everything around it through gravity. When astronomers measured how the universe's expansion rate is changing, they expected to find it slowing down due to gravity. What they found instead was that the expansion is accelerating. Something is pushing space apart. Something with energy, but no matter. Something everywhere, in every direction, growing stronger as the universe grows. And nobody knows what it is. Right now, without any conscious effort from you, roughly 86 billion neurons in your brain are firing electrical signals. Each signal is a tiny wave of charged particles rushing across a cell membrane. Each wave lasts about 1 millisecond. And from the coordinated pattern of those waves emerges everything you have ever thought, felt, remembered, or imagined. Your brain is an electrical machine. It runs on energy the same way any circuit does, except that the circuit rewires itself constantly in response to experience, and the signals it produces generate consciousness. Neurons communicate at junctions called synapses. When a signal reaches the end of one neuron, it triggers the release of chemical messengers, called neurotransmitters, into the synapse gap. Those chemicals drift across the gap and bind to receptors on the next neuron, triggering or suppressing a new electrical signal. Every thought you have is a cascade of these electrochemical events moving through networks that span billions of connections simultaneously. The electrical signals themselves are powered by ion pumps in the cell membrane. These pumps use adenosine triphosphate, your body's energy currency, to push sodium ions out of the cell and pull potassium ions in. This creates a charge difference across the membrane, positive outside and negative inside, like a tiny battery sitting at rest. When the neuron fires, channels open, and the ions rush back across the membrane, briefly reversing the charge. That reversal is the electrical signal. It travels along the neuron like a wave. The energy cost of all this is significant. Your brain makes up about 2% of your body weight, but it consumes roughly 20% of your total energy at rest. During intense mental effort, that number can climb higher. The fuel is glucose, delivered by blood. Cut off the blood supply for even 10 seconds, and consciousness begins to fade. Cut it off for 4 minutes, and brain cells begin to die. Memory forms through a process called synaptic potentiation. When two neurons fire together repeatedly, the connection between them strengthens. The synapse becomes more efficient at transmitting signals, energy gets invested in building larger receptor structures, more reliable chemical release mechanisms, and sometimes entirely new synaptic connections. A memory is a physical change in the brain's wiring, maintained by continuous energy expenditure. This means forgetting is also an energy story. Unused connections weaken because the brain stops investing energy in maintaining them. The synapses shrink, the proteins break down, the memory fades. Your brain does not store memories passively like files on a hard drive. It actively reconstructs them every time you recall something, spending energy in the process. Consciousness itself may be the most profound energy mystery of all. Scientists understand how neurons fire. They understand how signals propagate. They can map activity in the brain during different mental states with remarkable detail. What they cannot explain is why that activity produces subjective experience. Why do the electrical signals feel like anything from the inside? Why is there something it is like to be you, looking at the world through your eyes, rather than just a biological machine processing data in the dark? This question, called the hard problem of consciousness, has no agreed answer. Some researchers think consciousness will eventually be explained purely in terms of information and energy flow. Others think something fundamental is missing from our understanding of physics itself, and that gap between understanding the physical process and understanding the experience it produces leads directly to the deepest question physics currently faces. A question about whether energy has a physical reality at all, or whether it is something the human mind invented. Take a spring, compress it until the coils are nearly touching, lock it in that position. Now weigh it. According to Einstein's equation, that compressed spring should weigh slightly more than it did before you compressed it. The stored elastic energy added mass to the object. The difference is so tiny that no bathroom scale could ever detect it. You would need the most sensitive instruments in the world to measure it. But it is real, and it has been confirmed. This is one of the most counterintuitive predictions of modern physics. We generally think of mass as a fixed property of an object. A spring is a spring. Its mass is its mass. But Einstein said that energy and mass are the same thing, and if you add energy to a system, you add mass. No exceptions. The numbers involved make the effect nearly invisible in everyday life. Compress a heavy steel spring hard enough to store 1 joule of elastic energy inside it. 1 joule is roughly the energy it takes to lift a small apple about 3 feet off the ground. according to Einstein's equation, that spring now has more mass by about 11 trillionths of a gram. That is roughly the mass of 100 million hydrogen atoms. Invisible, immeasurable, with ordinary tools. But physically real. Scale this up, and the effect becomes enormous. A uranium nucleus stores a tremendous amount of binding energy in the strong nuclear force. Because of that stored energy, the nucleus has more mass than you would get by simply adding up the masses of its individual protons and neutrons. This extra mass is called the mass defect, and it is directly measurable with modern instruments. When uranium fissions, the products weigh less than the original nucleus because some of the binding energy has been released. The missing mass became energy. The equation works perfectly. Batteries also demonstrate this principle, though again at a scale too small to detect without extreme precision. A fully charged battery holds more energy than a dead one. By Einstein's reasoning, a fully charged battery should have slightly more mass. The difference for a typical car battery is on the order of a billionth of a gram, far too small to weigh in practice. But calculations confirm it is there. The practical consequence of this principle runs through all of nuclear physics and particle physics. Every time you see a nuclear reaction in an equation, physicists account for mass before and after. The difference in mass on each side of the equation equals the energy released or absorbed. The bookkeeping is always exact. The equation never fails. Even the photons leaving the sun carry this principle into practice. Every photon emitted by the sun represents a tiny slice of the sun's mass converted into pure radiated energy. The sun is slowly losing mass as it shines. Over the entire lifetime of the solar system, the sun has converted a significant fraction of its mass into the light and heat that made life possible on Earth. The spring that weighs a little more when compressed is a mundane, almost boring illustration of a principle that connects the warmth on your skin on a sunny day to the nuclear fire at the center of a star. Energy and mass are interchangeable not as a metaphor or an approximation, but as a literal, measurable physical fact. And the clearest place to watch that exchange happen in real time is inside a particle accelerator, where scientists deliberately convert motion into matter and matter back into motion, over and over, billions of times per second. What comes out of those collisions goes far beyond what went in, and the results keep rewriting what physicists think matter even is. Beneath the Swiss-French border, buried about 300 feet underground, a tunnel runs in a circle 17 miles across. Inside, two beams of protons travel in opposite directions. Each proton accelerates until it moves at 99.9999% of the speed of light. Then the beams cross, and individual protons collide head-on. The collision lasts for a duration so brief it defies comparison to anything in ordinary life. And in that instant, the kinetic energy of two protons, each smaller than a billionth of a millimeter, releases enough concentrated energy to produce dozens of new particles, some of which had never existed anywhere in the universe since a fraction of a second after the Big Bang. This is the Large Hadron Collider, and what it does every second is convert energy into matter on demand. When two protons collide at close to the speed of light, their kinetic energy concentrates in the collision zone. The quantum fields in that region spike to enormous levels of excitation. Every field that couples to the available energy, meaning every field that the electromagnetic and nuclear forces can excite, flickers and produces particles. New protons, antiprotons, pions, muons, and dozens of other particles spray outward from the collision point. The particles that emerge were not inside the original protons. They came from the energy. The kinetic energy of the collision excited the surrounding quantum fields enough to produce new ripples, new particles. The protons were just the delivery mechanism for the energy. This process runs backward too. When a particle and its antiparticle meet, they annihilate. An electron and a positron collide, and both particles vanish. In their place, Two photons shoot outward, carrying all the energy that was stored in the mass of both particles. Matter becomes energy. The fields smooth out in one place and create waves in another. In the 1990s, physicists at colliders around the world produced conditions that had not existed since the universe was less than a millionth of a second old. At those energies, matter and antimatter particles appeared and disappeared so rapidly that distinguishing them was impossible. The universe in its earliest moments was a dense soup of interchangeable energy and matter, constantly converting back and forth. The Higgs boson was confirmed at the Large Hadron Collider in 2012. The Higgs boson is a ripple in the Higgs field, which fills all of space. The interaction between this field and other particles is what gives them mass. Without the Higgs field, particles like electrons and quarks would be massless and would travel at the speed of light without ever combining into atoms. Matter as we know it would not exist. The mass of a particle is a measure of how strongly it interacts with the Higgs field. Heavy particles interact strongly. Light particles interact weakly. Photons do not interact at all, which is why they have no mass and travel at the speed of light. Finding the Higgs was finding the mechanism behind mass itself. And if mass is just an interaction with a field, and if energy and mass are the same thing, then at the deepest level, everything reduces to fields interacting with other fields. Energy is not something the fields contain. Energy is what the fields are doing. But outside the controlled environment of a collider, at the scale of the entire universe, something has gone deeply wrong with our understanding of energy. Something is filling the cosmos with power from no identifiable source. And the more the universe expands, the stronger it gets. In 1998, two independent teams of astronomers were studying exploding stars called supernovae in distant galaxies. Supernovae are useful to astronomers because they release a known amount of light. By measuring how bright a supernova appears from Earth, you can calculate exactly how far away it is. Both teams were using this technique to map the expansion of the universe and figure out whether gravity was slowing it down over time. Both teams found the same result, a result so unexpected that several researchers initially assumed they had made an error. The universe was not slowing down, it was speeding up. Distant galaxies were receding from us faster than nearby galaxies. The expansion of space was accelerating. Something was pushing the universe apart, overcoming the gravity of all the matter inside it and adding speed to the expansion. The further back in time the astronomers looked, the smaller this effect appeared. Over the last several billion years, the acceleration has been growing stronger. This force was named dark energy. The name captures two facts. It involves energy, and we have no idea what it is. Dark energy makes up roughly 68% of the total energy content of the universe. All the matter you can see, every star, planet, gas cloud, and galaxy in the observable universe, adds up to about 5%. Another 27% is dark matter, which is also invisible but at least exerts gravity. The remaining 68% is dark energy, and it behaves unlike anything in known physics. Dark energy does not dilute as the universe expands. Normal matter and energy spread out as space grows, becoming less dense. Dark energy maintains a constant density as space expands. As the universe grows bigger, the total amount of dark energy grows proportionally with it. This violates every intuition about how energy works. It means dark energy is not contained in objects or particles. It is a property of space itself. The simplest mathematical description of dark energy is called the cosmological constant. Einstein actually introduced a version of this in his equations of general relativity, then removed it when he thought it was unnecessary. In its current form, the cosmological constant represents a fixed energy density that belongs to the fabric of space-time. Space has energy just by existing. More space means more total dark energy. But where does this energy come from? Every physical system requires a source. Energy does not appear without a cause, and dark energy appears to violate this. It emerges with expanding space, tied to nothing, sourced from nothing we can identify. One candidate explanation connects dark energy to quantum vacuum energy. The ground state energy of quantum fields that the Casimir effect demonstrated is real. The problem is that when physicists calculate how much vacuum energy quantum field theory predicts, the answer is about 120 orders of magnitude larger than the dark energy density astronomers actually measure. 120 orders of magnitude means a 1 followed by 120 zeros. It is the largest discrepancy between theory and measurement in the history of science. This failure has no clean resolution. Something is either deeply wrong with quantum field theory's predictions at large scales, or something is cancelling almost all of the vacuum energy down to a tiny residual, or dark energy is something completely different from vacuum energy. All three options are uncomfortable. And this is where energy conservation itself starts to bend. Because if dark energy grows with the universe, where is the new energy coming from? The first law of thermodynamics says energy cannot be created, but the universe is creating it. Every second, as space expands, dark energy increases. The law that has never been broken in any lab on Earth may be breaking across the entire cosmos. And the reason why takes us into the deepest and most unsettling territory in all of physics. Every physics teacher tells students the same thing. Energy cannot be created or destroyed. The first law of thermodynamics. A rule with no exceptions. A rule you can bet the universe on, and then you actually bet the universe on it, and it fails. On small scales, energy conservation works perfectly. Isolate any system you want. A chemical reaction in a beaker, a nuclear explosion in a test chamber, a supernova measured across light years. Add up the energy before and after. The totals match every single time. But the universe is not an isolated system in any conventional sense. The universe is expanding. Space-time itself is stretching. And when space-time stretches, things happen to energy that have no parallel in ordinary physics. Consider light traveling across the universe. A photon emitted by a galaxy 2 billion light-years away has been traveling through expanding space for 2 billion years. As the space it travels through stretches, the photon's wavelength stretches with it. A longer wavelength means lower frequency. Lower frequency means less energy. The photon arrives at our telescopes with measurably less energy than it started with. Where did that energy go? Physicists have a technical answer. In general relativity, energy is conserved locally. In any small region of space over a short time, the books balance. But globally, across the entire universe, over cosmic timescales, there is no agreed definition of total energy that remains constant. The mathematics simply does not produce a conserved global energy quantity when space-time is curved and expanding. This is not a minor technical footnote. It is a fundamental gap in our understanding. Energy conservation, the most reliable law in physics, works perfectly in every controlled setting we have ever studied, but it lacks a rigorous formulation when applied to the cosmos as a whole. The expansion of the universe transfers energy in ways that have no clean accounting. Photons lose energy to redshift, but that energy does not show up somewhere else in a trackable form. It does not heat matter. It does not drive particle production. It appears to simply be absent from the universe's total energy budget in a way that has no clear explanation. Dark energy compounds the problem. As space expands, dark energy density stays constant, meaning total dark energy grows. New energy appears to enter the universe's accounting with every cubic meter of space that comes into existence. A straightforward reading of the first law says this is impossible, but the straightforward reading does not apply in the presence of a cosmological constant in a general relativistic framework. Some physicists argue that this is simply a matter of choosing the right mathematical definition. If you define energy carefully enough using the machinery of general relativity, you can construct something that is locally conserved, even in an expanding universe. Others argue this is a mathematical convenience that does not reflect physical reality. The honest answer is that physicists disagree. The community has not reached consensus on whether energy is globally conserved in our universe or not. The most fundamental law in physics sits in genuine dispute at the largest scale. And the reason for that dispute traces back to Einstein's greatest achievement. The theory that gave us the most accurate description of gravity ever constructed also quietly made energy harder to define than it had ever been before. In 1915, Einstein published the General Theory of Relativity. It described gravity not as a force between objects, like Newton had imagined, but as the curvature of space-time caused by mass and energy. Objects moving through curved space-time follow the curves. That curved path is what we experience as gravitational attraction. The theory was a triumph. It predicted that light bends around massive objects. Confirmed in 1919, it predicted that time passes slower in stronger gravitational fields. Confirmed by atomic clocks aboard satellites, it predicted the existence of black holes, gravitational waves, and the expansion of the universe. All confirmed. Every single prediction has held up. But Einstein's theory created a quiet crisis that has never been fully resolved. In classical physics and in special relativity, energy is defined cleanly. It is a quantity that can be calculated at any moment for any system. It has a specific value. You can add up all the energy in a region and get a number that stays constant over time if the system is isolated. Simple, reliable. General relativity broke this. In general relativity, space-time is not a passive background. It is a dynamic, flexible structure that curves and stretches in response to the matter and energy inside it. The problem is that this flexibility makes it impossible to define energy in a globally consistent way. Think of it this way. When you measure the energy of a moving object, you measure it relative to a reference frame, meaning relative to some chosen perspective. On a flat space-time, two different observers can agree on the total energy of a system as long as they account for their relative motion. But in curved space-time, no two points share the same reference frame in a simple way. The curvature mixes up space and time in ways that make energy definitions frame-dependent and location-dependent. Energy in general relativity becomes what mathematicians call a non-tensorial quantity in general spacetimes. This means there is no single mathematical object that all observers agree represents energy in a curved dynamic space-time. You can define energy-conserved quantities in special cases. For example, around a single massive object like a black hole that is not changing, energy can be defined cleanly. But in a universe that is expanding and in which space-time is changing everywhere simultaneously, the clean definition falls apart. This is not a solvable problem with current mathematics. It is a structural feature of the theory. General relativity and a globally conserved energy simply do not fit together naturally in a dynamic universe. The attempts to patch this include defining something called pseudotensors, mathematical objects that look like energy quantities in some coordinate systems but not others. These can make energy conservation work in specific useful situations, but physicists disagree on whether pseudotensors represent genuine physical quantities or just mathematical artifacts. What this means practically is that the universe does not guarantee total energy conservation across all of cosmic history. The rule that is held perfectly in every lab on every planet may be a local approximation of something more complicated, something that breaks down when space-time itself is allowed to change. Einstein knew about this problem. He worked on it. He never solved it. Every major figure in theoretical physics since then has taken a pass at it. Nobody has produced a universally accepted answer. And this problem connects directly to the question that philosophers and physicists have been circling for decades. If energy cannot be cleanly defined at the largest scales, if it does not globally conserve in a changing universe, is it even a real thing? Or is it just a useful idea humans invented to help predict the behavior of small systems? That debate is older than quantum mechanics and has not gotten quieter. In 1964, the physicist Richard Feynman gave a series of lectures at Cornell University that were recorded and later published. In one of them, he addressed energy directly. He said that in physics, we have no knowledge of what energy is. He said the universe has a set of rules, and that one of the rules is that a number can be calculated before and after anything happens, and the number stays the same. We call that number energy, he said. But what it is, we do not know. This was not false modesty. Feynman was one of the sharpest scientific minds of the 20th century. He meant it literally. Physics has two ways of treating energy. The instrumentalist view says energy is a mathematical tool, a number in an equation that we define, calculate, track, and use to make predictions. It works extraordinarily well, but that does not mean energy exists as a physical thing, the way a rock or an electron exists. It is a bookkeeping device. Humans invented the concept, defined what counts as energy, chose the units, and built a system that has proven useful. The success of the tool does not prove the tool is made of something real. The realist view says energy is genuinely physical. When a photon travels through space carrying energy, something is physically there, moving through space. When a compressed spring stores energy, that energy occupies the spring in some physical sense. The fact that we can measure it, track it, and watch it convert between forms means it is as real as anything else in the universe. Both positions have serious defenders, and the debate is not purely philosophical. The answer changes how you think about what physics is actually doing. Consider the conservation of energy. In classical physics, conservation of energy follows from a deep mathematical theorem called Noether's theorem, developed by mathematician Emmy Noether in 1915. The theorem proves that every continuous symmetry in the laws of physics produces a corresponding conserved quantity. Energy conservation comes from the fact that the laws of physics are the same today as they were yesterday. If the laws do not change over time, energy is conserved. This is profound. Energy conservation is not a brute fact about the universe. It is a consequence of a symmetry. It exists because the rules of physics are time-independent. If the rules changed, energy conservation would break. This is actually what happens in an expanding universe, where space-time evolves. The laws of physics still hold locally, but the global symmetry breaks down, and so energy conservation breaks down with it. From this perspective, energy is not a substance floating around the universe. It is a shadow cast by a symmetry, a number that stays constant because of a deeper regularity. Remove the symmetry, and the number stops being conserved. It was always just a consequence of something else. This framing has led some physicists and many philosophers of physics to conclude that energy is not ontologically basic. It does not belong on the list of fundamental things that exist. It belongs on the list of useful mathematical constructs that describe regularities in the behavior of things that do exist. But here is the counterargument. Virtual particles produce measurable forces. Vacuum energy pushes metal plates together. Stored energy adds measurable mass to a spring. If energy were purely abstract, how does it produce these concrete physical effects? Something real has to be doing the pushing. Something real has to be adding the mass. The answer to that counterargument leads into the last great frontier of physics. A frontier where the definitions of space, time, matter, and energy may all collapse into something nobody has a name for yet. Cool an object down, remove heat, slow the atoms, do it more, do it again. Keep going until you reach the theoretical floor of coldness, the lowest temperature physically possible. Absolute zero, that is roughly minus 459 degrees Fahrenheit. At that temperature, classical physics says all motion stops, the atoms freeze in place. Everything goes quiet. Quantum mechanics says otherwise. At absolute zero, atoms do not stop moving. They cannot. The uncertainty principle forbids it. To have an atom sitting perfectly still at a perfectly defined location you would need to know both its exact position and its exact momentum simultaneously. Quantum mechanics prohibits that. So even at the absolute lowest possible temperature, atoms still jitter. They vibrate with a residual motion that cannot be removed by any cooling process. This residual motion carries energy. That energy is called zero-point energy. It is the minimum energy a quantum system can have, the floor, the absolute lowest rung on the energy ladder. And it is above zero. Every quantum system has it. Every atom, every molecule, every quantum field. Even in its ground state, energy persists. The universe at its coldest, quietest, most emptied out extreme still buzzes with a baseline of quantum activity that cannot be turned off. Experimental evidence for zero-point energy is solid. Liquid helium is the clearest example. At standard pressure, helium remains a liquid all the way down to absolute zero. Every other substance freezes into a solid because its atoms slow down enough for the forces between them to lock them into a rigid structure. Helium never freezes at normal pressure because its zero-point energy is too large. The quantum jitter is energetic enough to keep the atoms moving even at the lowest attainable temperature. You need to apply significant external pressure to force solid helium to form. The vibrational frequencies of molecules also reveal zero-point energy. When scientists analyze the spectrum of light absorbed and emitted by molecules, the pattern does not start at zero. Even the ground state of a molecule contains a half quantum of vibrational energy. This half quantum is the zero-point energy contribution, and it shows up in every molecular spectrum ever recorded. Zero-point energy also connects directly to the Casimir effect described earlier. The vacuum fluctuations responsible for the force between those two metal plates are manifestations of zero-point energy in the electromagnetic field. Empty space hums at its quantum minimum. That minimum is not nothing. This raises an obvious question. If empty space contains energy, and if that energy is real enough to push metal plates together, can it be used? Can zero-point energy be extracted and turned into something useful? Can you run a machine on the quantum hum of the vacuum? The answer, currently, is no, and the reason is deeply frustrating. Zero-point energy is the ground state. You cannot extract energy from a system that is already at its lowest possible state. To extract energy, you need a difference in energy levels, something above the floor that can fall to the floor. The zero-point energy is the floor. There is nothing below it to fall to. This has not stopped generations of enthusiasts from trying. The history of attempts to harvest zero-point energy is long, colourful, and uniformly unsuccessful. What those attempts revealed, however, was something important about the nature of energy itself, and the most ambitious of them led directly to one of the most expensive and persistent failures in the history of science. The idea is seductive. The vacuum of space is packed with energy. It is everywhere. It is unlimited. It costs nothing to access because it belongs to the fabric of space itself. If you could tap into it, the energy crisis would be over instantly. Every home, every city, every civilization could run forever on the limitless hum of empty space. No fuel, no pollution, no limits. For over a century, this idea has attracted inventors, researchers, and dreamers in roughly equal numbers, and it has produced, so far, exactly zero working devices. The problem is not ambition. The problem is physics. Zero-point energy is the ground state of quantum fields. To use energy, you need a difference between two states. A waterfall generates power because water sits high and falls low. A battery generates power because one terminal is at higher electrical potential than the other. Every energy source works by exploiting a difference. High energy state on one side, low energy state on the other. Energy flows between them, and you capture some of that flow. Zero-point energy has no lower state. It is the lowest state. There is nowhere for the energy to fall to. Surrounding your extraction device with zero-point energy on all sides means there is no differential. Energy cannot flow from the vacuum into your machine because the machine itself sits in the vacuum and shares its ground state energy. You would need to create a region with less energy than the vacuum ground state. The uncertainty principle says that is impossible. This point has been made clearly in peer-reviewed physics since the 1950s. The mathematics is not ambiguous. The ground state energy cannot be extracted in a thermodynamic sense because it represents the minimum entropy configuration of the field. Extracting it would require the field to drop below its minimum, which the universe forbids. Despite this, governments and private investors have spent significant money on zero-point energy research programs at various points in the past few decades. Some of these were driven by genuine misunderstanding of the physics. Some were driven by wishful thinking. A few were driven by outright fraud. The most famous of these programs involved a company called Blacklight Power, which spent decades claiming to have found a way to extract energy from hydrogen atoms by pushing their electrons below the ground state predicted by quantum mechanics. The process supposedly produced hydrogen atoms, called hydrinos, with electrons at energy levels lower than standard physics allows. Despite millions in investment and multiple rounds of claimed demonstrations, no independently verified energy production ever came from it. The physics community rejected the theoretical basis entirely. More recent interest in zero-point energy has come from fringe interpretations of the Casimir effect. The force between those metal plates is real, but the force does not represent extractable energy. Running the plates together releases a tiny amount of energy once, and then they are stuck together. Pulling them apart again requires putting more energy in than you got out. You cannot run a cycle. The Casimir effect demonstrates vacuum energy is real, not that it is harvestable. The failure of free energy schemes is not a failure of imagination. It is a success of physics. The laws are consistent, the ground state is real, and the impossibility of extracting it is itself a profound statement about the structure of the universe. But there is a theory that imagines energy at a level even more fundamental than quantum fields. A theory that says the fields themselves and energy itself might emerge from something so small and strange that it changes what space and time even mean. Every particle in the standard model of physics has properties: mass, charge, spin. Different particles, different properties. An electron has a specific mass and a negative charge. A quark has a fractional charge and a different mass. A photon has no mass and no charge, but carries spin. The standard model catalogues all of this precisely. What it does not explain is why each particle has the exact properties it has. Why is the electron's mass what it is? Why is its charge that specific number? String theory proposes a radical answer. All particles are the same thing vibrating differently. In string theory, the fundamental unit of reality is not a point-like particle. It is a one-dimensional string, an incredibly thin loop or strand of energy, smaller than anything physics can currently measure, roughly 100 billion times smaller than a proton. These strings vibrate, and the pattern of their vibration determines what particle they appear to be. A string vibrating in one mode appears as an electron. The same string vibrating in a different mode appears as a quark. Another vibrational mode produces a photon. Every particle in the universe is the same type of string playing a different note. Energy, in this picture, is the vibrational state of the string. A string vibrating at higher frequency carries more energy. A string vibrating at lower frequency carries less. Mass is a form of vibrational energy that is locked into the string's pattern. Charge is a property that emerges from how the string's ends behave. Everything derives from the vibrational energy of a single type of fundamental object. This is elegant, startlingly so. One object, one set of vibrational modes, and you can, in principle, derive every particle that has ever been observed. The diversity of matter and energy reduces to a single vibrating string playing different frequencies. String theory also resolves one of physics's most persistent problems. Quantum mechanics and general relativity are the two most successful theories in science, and they are fundamentally incompatible. Quantum mechanics describes the behavior of the very small using probabilistic fields. General relativity describes the behavior of the very large using smooth, continuous space-time. When you try to apply both simultaneously, as you must near a black hole, or at the Big Bang, the equations produce infinities. The math breaks down. String theory dissolves the incompatibility. Because strings have physical extent, the point-like infinities that quantum gravity produces disappear. The string's finite size smooths out the collision that produces infinite results. String theory naturally includes a particle called the graviton, which carries the gravitational force, something the standard model conspicuously lacks. The problem is evidence. String theory requires the universe to have between 10 and 11 spatial dimensions, most of which are curled up so small they are completely undetectable at any energy level current or foreseeable technology can reach. It produces a mathematical landscape of possibilities so vast that nearly any observation could be accommodated by some version of the theory. Critics argue this makes string theory essentially untestable. As of right now, no experiment has confirmed or denied string theory. It remains the most mathematically rich attempt to answer the deepest questions about reality. But it sits at the edge of what physics can verify. If string theory is right, energy is not a property of particles or fields. Energy is what strings are. The universe is made of tiny vibrational loops, and everything, matter, forces, space, time, is an expression of how those loops move. That would be the deepest possible answer to the question of what energy is. But to get there, physicists must first solve a problem that has blocked progress for decades. A problem that sits at the intersection of quantum mechanics and gravity, and that no theory, not even string theory, has fully cracked. Two theories run the universe. Quantum mechanics handles the very small. General relativity handles the very large. Both are tested to extraordinary precision. Both work perfectly in their own domains. And when you try to use them together, the math produces answers like infinity, which in physics means the calculation has broken down and something is wrong. This is the problem of quantum gravity, and it is the reason physicists still cannot write a single definition of energy that works from the scale of a quark to the scale of a galaxy cluster. In quantum mechanics, energy comes in discrete chunks. A quantum system jumps between energy levels. The transitions are abrupt and probabilistic. The fields are uncertain and fluctuating. Space and time are a fixed background stage on which quantum events play out. In general relativity, energy is smooth and continuous. It curves space-time. Space-time tells matter how to move. Matter tells space-time how to curve. The two are locked in a continuous dance. Space and time are not a fixed stage. They are active participants that bend and stretch in response to whatever energy they contain. These two pictures are built on opposite assumptions. Quantum mechanics needs a fixed space-time background to define its wave functions. General relativity says space-time is dynamic. Put them together, and neither one works. The background that quantum mechanics requires is forbidden by general relativity. The smooth, continuous space-time that general relativity describes is shredded by quantum fluctuations at small enough scales. At the scale of a black hole's center, or at the moment of the Big Bang, both theories should apply simultaneously. A tiny region of enormous energy density, where quantum effects cannot be ignored, and where gravity is overwhelming. Every attempt to calculate what happens in those conditions, using both theories together, produces infinities. Nonsense. The calculation fails completely. Physicists call the scale where quantum gravity matters the Planck scale. It corresponds to lengths about 100 million billion times smaller than a proton. At that scale, the familiar concepts of distance, time, and energy lose their standard meanings. Space may not be smooth and continuous. It may be granular, made of discrete units the way matter is made of atoms. If space itself is quantized, then everything built on the assumption of smooth space-time, including general relativity's description of energy, needs revision. Several approaches are being pursued. Loop quantum gravity proposes that space is made of discrete spin network states, quantized chunks of geometry that replace the smooth fabric of general relativity. Energy at the Planck scale would be defined in terms of these discrete geometric units, rather than smooth fields. String theory, as described earlier, proposes to bypass the problem by replacing point particles with extended strings, which smooths out the infinities. But string theory has not yet produced quantitative predictions that experiments can test. What this means for energy specifically is that every definition of energy we have is provisional. In classical mechanics, energy is defined in one way, in quantum field theory, in another, in general relativity, in another. These definitions agree in the large overlapping region where everyday physics happens. But at the edges, where scales are extreme, the definitions diverge. We do not have a fundamental theory from which all these definitions flow as special cases. The absence of a quantum theory of gravity is not just a gap in academic knowledge. It means that our understanding of the universe's earliest moments, of what happens inside black holes, and of whether energy is conserved at the deepest level of reality, is genuinely incomplete. Not approximately complete. Genuinely, fundamentally incomplete. And that incompleteness points toward a final question, a question that might be the most important one physics will answer in the coming century. What does it mean for us if we ever do crack it? Every technology you depend on was built on a partial understanding of energy. The power grid, the internal combustion engine, the nuclear reactor, the solar panel, the smartphone in your pocket. All of it engineered using rules that physicists know work, even while those same physicists cannot agree on what energy fundamentally is. That gap between functional knowledge and deep understanding has been the engine of science for centuries. Humanity did not need to know what fire was made of to cook food, but understanding combustion at the chemical level unlocked the Industrial Revolution. We did not need to know what matter was made of to build machines, but understanding atoms unlocked electronics, medicine, and nuclear energy. Every time physics has gotten deeper into the nature of something, civilization has leaped forward. The understanding of energy is not yet at its foundation. We are still working with definitions that break down at the extremes. We have powerful rules, the conservation laws, the thermodynamic principles, quantum field theory. These rules produce technologies of extraordinary precision, but the question of what energy actually is, at the most fundamental level, remains open. A complete theory of quantum gravity would likely resolve this. Such a theory would describe space, time, matter, and energy in a single unified framework. It would tell us how energy behaves at the Planck scale, where current physics goes silent. It would explain whether energy conservation holds globally across the universe, or only locally. It would tell us what dark energy actually is, and why the vacuum energy predicted by quantum mechanics differs so drastically from what astronomers measure. The applications of such a theory are impossible to fully predict, because every previous deep unification in physics produced applications that nobody anticipated. Maxwell unified electricity and magnetism in the 1860s. This was an abstract theoretical achievement. Within decades, it produced radio, radar, and eventually every form of wireless communication. Einstein's special relativity was pure theory in 1905. By the mid-20th century, it was essential for nuclear power and nuclear weapons. Quantum mechanics was considered philosophically puzzling and practically useless in the 1920s. It became the foundation of every semiconductor, every laser, and every modern computer. A theory that unifies quantum mechanics and gravity and that fully defines energy at every scale would represent a leap comparable to any of those. The specific technologies that would follow are unknowable in advance, but the pattern of history suggests they would be transformative beyond current imagination. There is also the philosophical dimension. Humanity's sense of its place in the universe has shifted with every major scientific revolution. When energy was understood as a conserved quantity, it implied a universe governed by reliable rules. When Einstein showed mass and energy are equivalent, it implied that matter is not what it appears. When quantum mechanics showed that particles are field excitations and that the vacuum is energetic, it implied that empty space is not what it appears either. A final understanding of energy would almost certainly imply that reality at its deepest level looks nothing like what our everyday senses report. The solid table, the glowing screen, the warmth of sunlight, all are sophisticated patterns in fields that may themselves be expressions of something even more fundamental, something that does not yet have a name in human language because no human has yet seen it clearly enough to name it. The paperclip on your desk holds the energy of a weapon that reshaped history. The empty space in this room hums with quantum fluctuations that push metal plates together without touching them. Your thoughts are electrical signals consuming more energy per unit mass than a running car engine. And somewhere in the fabric of space, dark energy is accelerating the expansion of the entire universe toward an eventual cold, dark, diluted end from a source that no physicist alive can identify. The most powerful thing in the universe remains, at its core, a mystery, and the next chapter of that mystery belongs to whoever refuses to stop asking what it actually is.